Welcome back. We're going to pick up where we left off in video number 1. So make sure you've watched that before you watch this video. All right, so last time we talked about getting a strong set of hypotheses. The next step, what this video focuses on, is choosing the significance level, or alpha. So significance level, the purpose here is that we're going to set a standard of how strong the evidence is going to need to be for us to reject the null hypothesis. We're going to decide this in advance. Once we pick that level of evidence, we're not supposed to go back at the end and tamper with what we set up in the first place. So conventionally, most hypothesis tests use one of the following levels: 1%, 5%, or 10%. And that percentage is inversely related to the strength of the evidence. So it's actually the smallest significance level, 1% or 0.01, which will require the most evidence to reject the null hypothesis. Whereas at the other end of the spectrum, 10% is only going to require moderately strong evidence in order to reject the null hypothesis. And then, of course, in the middle, 5% is sort of a compromise, requiring strong evidence. Now, you might be asking yourself, well, why wouldn't we always want to require very strong evidence? Wouldn't we want to be very certain of the conclusions that we draw? Well, as you'll see in the video, there are a couple things that we need to keep in mind, and sometimes there's a trade-off involved. All right, so recall last time we said that any hypothesis test, one of two things is going to end up happening. Either we find strong evidence against the null hypothesis, so we reject it, and by process of elimination, say that the alternate hypothesis is true. Or if we don't find strong enough evidence, we won't be able to reject the null hypothesis. So we won't really know for sure what's going on. Two hypotheses would still remain. So humor me a little bit. I'm going to draw an analogy between a hypothesis test and a murder trial. So just like in a hypothesis test, a murder trial has two possible outcomes. Either the defendant is found guilty or they're found not guilty. In both cases, there's sort of the presumption of innocence. So the defendant is considered innocent unless the evidence proves otherwise. Similarly, in a hypothesis test, often people are going about their daily lives under the assumption that the null hypothesis is true. For instance, if a car manufacturer says that their vehicle gets 30 miles per gallon, you're probably going to believe them unless there's some evidence otherwise. If there's not a lot of evidence in a jury trial, the verdict would be not guilty. Now, note they don't say innocent, which is sort of like how we don't want to accept the null hypothesis simply because we don't rule it out. If there is strong evidence in a trial, we rule out the prospect that someone is innocent and conclude instead that they're guilty. So that would be analogous to when we reject the null hypothesis, leaving one hypothesis left, and we could conclude that the alternative is true. Lastly, and the focus of this video really, is that in both cases, we hope that the vast majority of the time the correct verdict is reached. But occasionally there may be a mistake where the verdict of the trial or the test does not match up with what's actually true. Okay, so let's take a look at an example of a hypothesis test where the possible outcomes, if we make a mistake, are sort of asymmetric, that one possible mistake is a lot more dangerous than the other. All right, so the Food and Drug Administration has a limit for the amount of mercury that's allowed to be present in fish that are going to be eaten. So that limit is 1 part per billion. We're going to consider a data set where we have measurements of this mercury concentration from largemouth bass in 53 different Florida lakes. And the idea is to do a hypothesis test to find out, and is there convincing evidence, strong enough evidence, that the mean mercury concentration is below that safe limit. Okay, so a bit of review. Pause the video if you need to. Think about what parameter would be relevant to test here, and how would you write your hypotheses using symbols. All right, so here we're measuring the amount of mercury in the fish. So that's a numeric quantity. So it'd be relevant to test the mean. The mean mercury concentration among all largemouth bass in Florida lakes. So to the null hypothesis, recall we need some sort of equal statement. Let me flip back a sec. So I picked 1 because we have this threshold. The Food and Drug Administration says that 1 part per billion is okay. So that's the threshold with that we don't want the mercury concentration to be above. So that would be the number that we're going to compare this mean against. And the null hypothesis always has to use the equal sign. In the alternative hypothesis, we got to be careful about the wording here. The question said, is the concentration below the safe limit? So that's a less than type situation. So we're going to test the mean is less than 1. It's below the safe limit. Okay, so think of that little 2-column flow chart. What are the possible outcomes or verdicts in this situation? And sort of describe, in what scenario would that verdict be correct or accurate? Well, one thing that might happen is that the null hypothesis is rejected, which leads us to support the alternative hypothesis. So that would be the correct outcome if, in these Florida lakes, the true mean concentration really is below 1. Okay, another possible outcome is that the null hypothesis is not rejected. So that would be the correct thing to do if the mean concentration really wasn't below 1. However, there are some other things that could happen. We call those errors. All right, so this little table is set up. We have 2 rows showing, well, what does the test say? Every test is either going to fail to reject the null or reject the null. And in the columns, but what's really true? If we could measure every fish that's out there, is the true mean really less than 1 or not? Okay, so if the null hypothesis is really true and we don't reject it, that's the accurate outcome. Smiley face there, everything is good. Similarly, if the alternative hypothesis is true and we're able to support it, well, that's good as well. No problem there. However, if we're in one of these other cells, an error reflects that the test is concluding something that's not accurate. And there's 2 different flavors of error, which we call a type 1 and a type 2. Okay, so type 1 error is that the null hypothesis really is true, yet our test rejects that. All right, so this can be thought of as a false positive. We think that something's going on, but really it isn't. The nice thing about this error, though, is that we get to choose at which relative frequency we're willing to accept that would occur. And that's symbolized by a quantity alpha. So remember those percentages from the beginning, 1%, 5%, 10%? Those are the significance levels, or alphas, indicating that we're willing to accept that a type 1 error would occur in 1% of samples, 5%, or 10% of samples. Again, you're probably thinking, well, why not go with a small number? Why wouldn't you want to minimize this type of error? Or why not even set it to 0? Well, that's because we've got to worry about the opposite situation, the type 2 error. So that's when the alternative hypothesis is actually true, yet we're not able to support it. So that the type 2 error is a false negative. We fail to detect that something's really going on. There is truly a difference, and we don't know about it. So often that represents a missed opportunity or missed information. And how often will that happen? Well, its relative frequency is described by another Greek letter, beta. And the thing about beta is it's inversely proportional to alpha. So if we pick a really small alpha, say we want to minimize type 1 error, we have to live with the consequence, which is that beta is going to be higher. That is, if we make a very stringent standard for evidence, there's going to be a lot more misses where we can't show that amount of evidence. Okay, so there's a trade-off here. We've got to consider, which is more important. Is it avoiding a type 1 error, or is it avoiding a type 2 error? Sometimes it doesn't really matter, and we might just choose to pick the middle value. But if one type of error is worse, we're going to want to steer towards one end of the spectrum or the other. Okay, so back to these fish. So we were testing that the mean mercury is less than 1 part per billion, which is the safe limit. A type 1 error would be that we conclude it really is below 1 when it's actually not. Now, would that be bad? Kind of take the worst case scenario. It'd be a little bit of a worry wart here. Well, if we think the mercury is safe and it's actually not, probably fishing is going to be allowed. People might end up eating fish that is too high in mercury, which is a poison. It can cause birth defects and brain damage and all sorts of bad things. All right, what about the other error? If we fail to detect that the mercury is actually below 1, and it really is. So that is, the fish are safe, but we don't know about it. Presumably, if we do some testing of these fish and we're not able to show that they're safe, the cautious person wouldn't eat them. So they're missing out on a chance to eat some fish that actually would be all right. But, nobody's injured or there's no major economic consequence to this. Okay, so in this case, the risk is pretty asymmetric. A type 1 error is much more dangerous in its consequences than a type 2. So it'd be logical to try to minimize the rate of type 1 error. And we wouldn't worry too much about the rate of type 2. Okay, so that's the sort of line of thought that we're going to use to pick our significance level. All right. So that small alpha says that we want to minimize how often a type 1 error would occur. So for instance, we want to minimize the chance that people eat fish that's too high in mercury. On the other hand, if we had a different situation where a type 2 error was very dangerous or expensive, we would want to go in the opposite direction and pick a large alpha. And the middle one, it's sort of like Goldilocks and the Three Bears. It's kind of balancing those two, where maybe neither a type 1 nor a type 2 error is especially bad, or they're equally bad, perhaps. Okay. So I might have already spilled the beans on this one, but in this case, to minimize the chance that people eat the fish that's too high in mercury, we would want to use the small alpha. Okay, we do this in step 2 before any calculations for the test. The idea being that once this is set, it's bad statistics or it's unethical to go back and tamper with it later. All right, let's take a look at one more scenario. Bit of a meme for you guys. All right, so hopefully you got a little chuckle there. Now, this isn't quite a hypothesis test, a pregnancy test, but we can still think about the types of error and the consequences of those error types. So which of these might be more dangerous? have more severe consequences. And in light of that, if this were a hypothesis test, which significance level would you choose? So think about that. All right. So suppose this grandpa on the left is told that he's pregnant and that he should take certain precautions, like start taking prenatal vitamins and abstain from smoking and drinking. Uh, is that going to cause any huge amount of damage or have any catastrophic consequences? I would say no. Those are all kind of healthy things that you could do. Maybe they'll improve his overall health, and I'm sure within at least the next 9 months, he'll figure out eventually that he's not actually pregnant. On the other hand, the lady on the right, if she believes that she's not pregnant, she might continue to, go drinking, or she might probably not take prenatal vitamins. She might eat raw sushi, and all those things could potentially be dangerous to the fetus that she doesn't actually know that is developing inside of her. So this would be a case where a type 2 error is more dangerous. Okay, so unlike the fish example, we've got the opposite situation. So in order to minimize the rate of type 2 error, we want beta to be small. Now, we don't get to pick beta, we get to pick alpha. So alpha is going to behave essentially in the opposite manner. So to get a small beta, we want to pick a large alpha. So, if this were a hypothesis test, the pregnancy test, we would want to use the 10% significance level. All right, coming up in part 3, we're going to see the specifics of how to do our calculations for a one sample test of proportion.